Hi there, in this video we're going to be talking about approximating the binomial distribution with the normal distribution. So because of the nature of the binomial distribution and its formula, when n is very large in this form here, so x is binomial distributed with n and p, when n is large, it can be really difficult to compute. So instead of doing that really hard computation, we can approximate it with the normal distribution, which is a lot easier to compute. So let me just read this out. So suppose a random variable x follows a binomial distribution with n and p. And if these two conditions are true, so if n is sufficiently large and p is very close to 0.5, we can approximate x with the normal distribution. And the parameters we put into the normal distribution are, for the mean, it's just np. And then for the variance, it will be np multiplied by 1 minus p. Sometimes you can even see this as being q. So sometimes it's written like that. But yeah, all we need to do is check that these conditions are true, and then we can approximate this binomial with this normal distribution. But before we can do any examples on this, we need to learn what continuity corrections are. And continuity corrections arise when we go from discrete data to continuous data. So with the binomial, for example, you only have probabilities at discrete values. So for example, it could be the integers, like that, for example. But with the normal distribution, if I draw it on here, because it's continuous, it'll look more like a curve. So we can still have our 1, 2, 3, 4, 5, but it'll look like that, for example. So now the issue with that is, for example, let's say we have a probability, a binomial distribution, and then we want to figure out something like px equals 4, right? So here, with the binomial, we just look at that probability at 4, so that would be okay, because it's discrete data and we get a value. But if you remember, with the normal distribution, the probability is the area under the curve. So x equals 4 is just this sliver here. And a line doesn't actually have any area. So it would actually give you 0. So you might be wondering, how can we figure out what x equals 4 is? Because it works in discrete, but with normal, it is completely different, and it equals 0 every time. Well, what we can do is we can use a continuity correction, which is, instead of getting what equals 4, we can actually just use everything that rounds to 4. So from 3.5, from 3.5 to 4.5, right? So this will equal, it's like if we had a number line like that. This is everything that 4 is spread out on. So from 3.5 to 4.5. So that's how we can use a continuity correction. And if you have a PD function on your calculator, that's what it does. It finds a continuity correction. So that's how it works with PD. But how does it work with CD and CD both less than or greater than, or less than or equal to? Well, I'll show you. So if we have x is less than, or I won't say 8, I'll keep it as 4 for now. So if we think about the number line again, I'll do it in a different color. So we want everything that's less than 4. So normally with a binomial, it'll be everything less than or equal to 3. But because we want to do a continuity correction as well, we want to keep this bit because everything up to 3.5 rounds to 3. So instead of that, we'll have probability of x is less than 3.5. Right? But when we want, for example, less than or equal to 4, for example, we want this bit here. But again, we want to get that top bit. So it would be less than or equal to 4.5. So when it's less than or equal to, we add 0.5, but when it's just less than, we take away 0.5. But if you think about it with the number line, it becomes a lot easier. And you don't need to memorize a bunch of things. Okay, so let's do this example to begin with. So it says if x is binomially distributed with n equals 80 and p equals 0.4, use a suitable approximation to find these 4 probabilities. Because it says approximation here, we know that we're meant to be using the normal distribution. If it didn't say approximation, then the question might be looking for us to actually calculate the binomial, using like the binomial formula. Okay, so let's start by figuring out whether we can actually approximate this. So if we look back at our 2 conditions, we want n to be sufficiently large and p to be close to 0.5. Well, p is 0.4, so that's pretty close, and n is 80, which is large enough to do the approximation. So let's do it. We want to get a normal random variable y with np times by 1 minus p. Yeah. So what we'll get is, well, n times p is 80 multiplied by 0.4, which will give us 32. And then we want 80 here, if I write it, 80 times by 0.4 times by 1 minus 0.4, which is 0.6. And that will give us 19.2 as our variance. Okay, so now that we found our random variable, our normal one, we can start and figure out this first one. So px equals 37. But remember, we now need to use continuity corrections to get from the binomial variable to the normal one. So what we can say is this is approximately, so that's what you can say when you're saying it's around about, the same probability as, well, y being from anything that rounds to 37. Like so. If you put that into your calculator, or use any other method of your choosing, you will get 0.0475. So for II, we have x is less than 45. Now, what a good method to always use with these are number lines and to visualize them on a number line when doing your continuity corrections. So x being less than 45 is the same as x being less than or equal to 44. Like that. And what we want to do is we want to include everything that rounds to 44 as well. So we're already including this bit, but we also need to include this bit here to 44.5. So what we get for a normal variable is a probability of x being less than 44.5. Or, my bad, y, because we're using the normal variable. It's very easy to make labeling mistakes like that, so be careful. So yeah, we can also use that, and we can put that into our calculator or look it up on a table or whatever, and we will get 0.9978. And it doesn't really matter what I do here, so it could be equal to as well, or here it could be equal to, but because in the normal distribution it's continuous, and so any instance of a number is equal to 0, it won't actually change the probability. Okay, so let's try the probability of x being greater than or equal to 40. So again, let's get our number line out. This time we've got 40, 41, and 39. And we want greater than or equal to 40, so that way. But remember, we also want to keep this bit here, right? So from 39.5 onwards. So we can approximate that to be y is greater than or equal to 39.5. And if you put that in, you'll get 0.0435 like that. And finally, we want to find this probability here. So this one's a bit tougher. So let's get our number line out. I'll do this one down here. So we have 32, 33, 34, and 35. So what we want to do is, with the binomial, we will do greater than 32, or we can say greater than or equal to 33 to 35, like that, right? So what we can do is, actually, let's include that. So for our continuity correction, we need to do up to 35.5 and down to 32.5. So again, it's common notation to keep the values the same, so we wouldn't or the symbols the same, sorry. So it'll still be a greater than, and still be a greater than or equal to, just with our new bounds. And if you put that in, you will get 0.2424. Okay, so let's say that p isn't close to 0.5. So actually, the approximation will actually still work if np and n times 1 minus p are still bigger than 5. Bear in mind that's not 5 factorial, that's just 5. So, yeah, so that condition actually doesn't need to be true. As long as if n is large enough so that these two values are bigger than 5. Okay, so let's start with this example. So it says, on average, only 23% of robin chicks survive to adulthood. If 80 robin chicks are randomly selected, use a suitable approximation to find the probability that at least 30% of them survive. So, off the bat, we can see that this is a binomial distribution. We got a probability there and the number there. So we can write it like this. So our number is 80, our n is 80, and our p is 0.23, like so. And you can see that p actually isn't very close to 0.5 here. But because it says approximation as well, we know that that's what they want us to do. So let's find out what NP is. So NP is 80 times by 0.23. And that is 18.4. And that's greater than 5. So that checks out. And then n times by 1 minus p is 80 multiplied by 0.77. And that will give us 61.6. That's definitely bigger than 5. So we can use y, which is distributed normally, with 18.4 being our mean, and our variance being, if you multiply all of the values together, you'll get 14.168, like so. So now what we can do is we can figure out what it wants us to what it's asking of us with this normal variable. So we want to find the probability that at least 30% of them survive. So let's figure out 30% of 80. So 80 times 0.3, well, that's 24. So hence we want the probability of x being at least 24, like so. But we want to approximate that. So using the continuity correction, if we got our number line out like that, so we want anything greater than or equal to 24, but we also want this bit, so we want that greater than or equal to 23.5, like that. And the probability you'll get is 0.0877. And then for B, it asks if the survival rate were instead 18%, estimate the probability that more than 3/4 of the 80 robin chicks would die. So now it's even further from 0.5. But again, let's see if it works. So NP, so now we have 80 times by 0.18. And that's 14.4, which again is greater than 5. And let's find n times by 1 minus p, which is 80 multiplied by 0.82. And we get 65.6. So that's also greater than 5. So we can see they're both greater than 5, so we can use this normal variable, because, my bad, I probably should have written out our new binomial variable. So let's not confuse it with the old one, so let's put a bar on top, or a hat. Let's do a hat. So now we still have 80, but our probability has changed. So now let's give y a hat. And now NP we already know is 14.4. And n times by 1 minus p times by m times p times 1 minus p is 11.808. So now we want to estimate the probability that more than 3/4 of the robin chicks would die. But remember this here, because our probability of success is when they survive, this X bar represents the number of robins who survive. So the probability that more than 3/4 of them will die is the same as the probability that 1/4 of them will survive. So instead of writing greater than or equal to 60, which is greater than or equal to the 3/4, we're going to write less than or equal to 20, or we can just write less than, actually. Doesn't it? Because if you think about it, we're looking at less than 20 because it doesn't say more. It just says more rather than 3/4 or more. So we can approximate that now to y. And again, if we use our number line, so 20 here, 19, 21, and we want less than 20, so less than or equal to 19. So we want this sliver here. So it will be 19.5. And that will give us 0.9311. Okay, thanks for listening.